We're looking at Chapter 5, Section 5.3 and 5.4. In this lesson, we'll determine the polynomial function that best approximates data, and we'll answer questions based on polynomial regression. So recall, in Chapter 5, we looked at 4 different types of polynomial functions. We looked at a constant function, linear, quadratic, and cubic functions, and we also investigated the graphs and equations for each of these different characteristics that was associated with each type of function. We are now going to continue through regression. And regression is a line or a curve of best fit developed through statistical analysis of the data. So what you would have done in class is you would have taken tables, these tables of values, and used some form of technology. You would have used maybe a graphing calculator or a computer program. You would have used technology, and you would have created the scatter plot. And using a regression function, whether it be linear, quadratic, or cubic, you would have developed a line or curve of best fit. And it would also give you the function that best describes the data, that would give you a function or the equation that describes this line or curve of best fit. So what we'll do in this section is we'll take these graphs or these regression functions and we'll answer questions based on the characteristics that we've learned in this section. So in this chapter, of course, as with the rest of the chapter, we'll look at 3 types of regression: the linear regression, a quadratic regression, or a cubic regression. So regression, a line best fit, is a straight line that best approximates a trend in a scatter plot. We will also see curve of best fit, which is a curve that best approximates a trend in a scatter plot. We are going to interpolate data, and we're going to extrapolate data. To interpolate, you have to use an estimated value within the domain of a set of data based on the trend. And to extrapolate, we have to use the process. It's the process used to estimate a value outside the domain of a set of data based on a trend. So let's jump right into an example. We have here, and as with the questions you will see, the graph shows a cubic regression. You will be told what type of regression is shown of an average price of gasoline per liter for the selection of years after 1979. So it also gives you, with the regression, it will also give you the regression formula. And you will have to answer questions based on this. We know it's a cubic regression, so any characteristics that came with a cubic function, what we learned with cubic functions, we'll have to apply to this scatter plot. For example, we can look at the domain, and in this case, the domain is the years after 1979, and we can see the years after 1979 under consideration. We can say that n is greater than or equal to 0, 0 being year 1979. The range, of course, in this graph will be the cents per liter. Okay, that's the range. That's the range values of cents per liter. And it looks to me like in 1979 it was 20 cents per liter. So it'll be above 20 cents per liter. And so our range will be P is greater than or equal to 20 cents per liter. The y-intercept of this function will be where the trend is when n equals 0, and the y-intercept will be 20. So we'll be able to answer questions like this, given a regression function. Another question we could be asked, of course, the y-intercept would also be 23.452 is the y-intercept of the function. If you look at the graph, it's around 20. And we know that because a constant tells us the y-intercept, and this is the regression function, that constant would give us our y-intercept. We could also say that the leading coefficient would be this one right here. So we have to answer questions based on the cubic regression using the skills we learned about the characteristics of cubic functions earlier. Let's have a look at another example. The graph shows a cubic regression of the price of gasoline per liter for a selection of years after 1979. So it will give us this function. What was the average price of gas in 1984? Well, 1984 is 5 years after 1979. So we may be able to use the table. We could see this being 6 years, so 5 years to help us estimate. And we can see that that would be about 45, 40, 46. If we look at 5 years, we look at the table right here. We could also take this 5 and use the equation. So we have P of 5 would be equal to 0.0123 5 cubed, subtract, n is 5. So we can use the equation to answer this question. And this would give us 44.9 cents per liter, which we know is about right since we estimated using the graph what it would be. It says estimate what year the price of gas was 80 cents per liter. So we would look at the graph and we would go 80 cents per liter. And we see that that could possibly be around 25 years. 25 years after 1979, which would be 2004. So once again, you could use the graph, use the equation to help you answer these regression questions. Let's have a look at another example. The results of a Math 3201 test and the time the student studied was recorded, and a linear trend was found. So here's the scatter plot. It also tells you what type of regression it is. So you would have to look at this function, and even though the equation is not there, you have to tell whether it's increasing or decreasing. And we can see that the trend is going upward, and we have an increasing function. What is the value of the constant? Once again, the equation's not there, but you could assume the value of the constant would be right here around 40. The domain in this case is the time the students took to study. So time cannot have any negative values. And we'll use t for time is greater than or equal to 0. The range is the test grade. The range would be the values of the test grade. And the range in this case would be 40 being the lowest. The grade is also less than 100%. We could see here that the grade is 40. We have student who studied for 0 hours getting 40. We have 45. We have maybe 57. So we have this. You have to identify this being the range. The following graph shows a quadratic regression. Notice that we're being told the type of regression again. You will always be told the type of regression function that you are investigating. For the volume of a pine tree and its diameter. So we have the curve of best fit right here. We're not given the equation, but we are given the curve of best fit. You may have to use the graph to answer a few questions. If the diameter is 15, what is the proximate volume of the pine tree? You can see that would be maybe around 35 using the trend. If the volume was 15, what would be the approximate diameter of the tree? You could probably say it would be around 11. And of course, the domain would be the diameter must be greater than or equal to 0. So let's have a look at another example. This graph shows how the number of breeding pairs in the park is dependent on the number of pedestrians per minute. Will the cubic regression function have a positive or negative leading coefficient? Since the graph is the shape of an N, not a backwards N, we could say they have a positive leading coefficient. Determine or approximate the number of breeding pairs if the number of pedestrians is 40. Here, if the number of pedestrians are 40, we're extrapolating the data. We're going outside the domain here now. So you take 40, and you see the curve is not drawn past 40. We'll estimate about 60 pairs. So in summary, when we're looking at regression questions, you'll be expected to answer questions using the graph of a regression. You'll be expected to substitute values into a regression function if it's given to answer questions. You'll be given the type of regression, so you don't have to worry about looking at graphs and determine what type of regression it is. You will be told the type of regression. And you will be expected to answer questions on the characteristics of the regression, like the characteristics we studied throughout Chapter 5, the y-intercept, leading coefficient, domain, range, increasing function, decreasing function, etc.